A very warm good morning to one and all. Myself, Dr. G. Haripriya, Convener, HOD of HNBS, Professor in Mathematics, Gates Institute of Technology. Welcome you all for day 6 of a one-week faculty development program on advanced materials, processing and characterization methods. Let's begin our session by introducing our honorable resource person, Abdul Azeem sir. It gives me an immense pleasure and honor to introduce a highly motivated and ambitious individual with passion for unraveling the mysteries of the universe in physics is none other than our today's speaker, Professor P. Abdul Azeem sir from NIT Warangal. Sir has completed his PhD in physics at SK University in the year 2002, PhD entitled Introduction to Luminescent Materials, Biomaterial Science and Technology. Sir has guided in doctoral thesis of relevant field. Sir has been teaching undergraduate and graduate level courses in physics for over 21 years. Sir is known for his engaging and interactive teaching style, encourages students to think critically and scientifically. Sir has published several international and national publications. Sir organized and attended workshops, conferences, seminars, and training programs. Sir actively involved and published numerical papers in top-tier physics journals and has received grants from prestigious funding agencies to support his research. Sir received awards and honors for his significant contributions to the field of physics and also elected as Associate Fellow of Telangana Academy of Sciences in the year 2019 with his wealth of knowledge. Sir performed additional responsibilities like Department Technic in Charge, Associate Dean and Coordinator, Graduate Outcome Committee, IRC Committee, and etc. Now, I hand over the session to Dr. Abdul Azeem, sir. Once again, hearty welcome, sir. Please carry on, sir.
Thank you, madam. Thank you for the nice introduction. Am I audible?
Thank you, sir. Welcome, sir.
Am I audible to you?
Sir, you are audible, sir.
Whether my voice is clear?
Yes, sir. It is clear, sir.
Good morning, all. I welcome all to this initiation. I thank the management of Gates Institute of Technology and the coordinates of this faculty development program for inviting me as a resource person to deliver a talk on the research activities which are happening in our lab, in our group. Right. Is visible?
Visible, sir.
Yeah.
Yes, sir. It's visible, sir.
So in the entire talk, I will try to, give you what are the activities are happening in our lab. And so I thank the research scholars. We are, working for me throughout this journey, right? So we are working in different fields. We started to work with luminescent material, and then we have extended our research to biomaterials, and then the supercapacitor applications, and then drug delivery. So like this, we are working in different areas, but our basic motto is to fabricate and design few amorphous and then crystalline materials for multifunctional applications. So here, the source, we have started with chemicals, a few chemicals, and then we have used the biomass material for deriving these or extracting the various material which are useful in the biomedical applications. So basically, we are working with the uh, recycling material, recycling waste like food waste, agro waste, industrial waste, and so on and so forth, as the sources of the material from which you are going to extract different types of material, and then with those material we are developing different types of structures, both amorphous as well as the crystalline material, and then we are working out for not only the amorphous, even the crystalline material for different types of applications. So it means we are trying to develop, fabricate, or design a material for not only for biomedical application, even for the display devices, then the anode material for supercapacitor applications, and then material for drug delivery uh, applications also. So in my talk, I'll try to discuss in detail about these things. So how much time I need to take so that I can able to I can discuss within that stipulated time. Can you hear me?
You are audible, sir.
Yeah, yeah. So how much time I need to take? 1 hour or 1.5 hour?
1.5 hours, sir.
Okay. So if there are any issues there, technically or anything, right, you can ask me. If there any doubt
Okay,
is
sir.
there, you
Yes, sir,
can.
we will intimate you, sir.
Sir, please change your slide, sir.
Yeah, I will change. I will change. I didn't change the slide. So if any issue is there, technically you can ask me. I can stop at any time. And if the if you have any doubt, you can ask me in the middle. No problem. You can stop at any time. You can ask. Right.
Okay, okay,
So
sir.
the title of my talk is Fabrication of amorphous and then the crystalline material for multifunction applications. As I mentioned earlier, we started to work with the biomaterials. So in the first part of my talk, I would like to discuss about the requirements for a biomaterial, and then how you are going to develop the biomaterials with glass, with the amorphous material, and then with the crystalline material, and then the few studies what you are doing in the lab, and then the fabrication of the biomaterial for drug delivery as well as the tissue healing applications. So before going to discuss about these things in detail, you must know what is a biomaterial. So biomaterial is a non-viable material used in medical device intended to interact with the biological system. See, if any part of the body is damaged partially or completely, you can able to replace it with this material. And uh, this material, whatever going to replace partly or fully, it should be safe, it should be reliable, it should be economical. And one more important thing we need to uh, think about is the how effectively the tissue is accepting physiologically your material. So if suppose some part of the bone is damaged, partly or fully, if you want to replace the bone with the biomaterial into the damage or into the or you can able to refill it or replace it. So first of all, we should test whether the body or the tissue is physiologically accepting this material or not. So that is very very important and one thing we need to remember. And one more thing is this we can able to use to replace partly or completely the disease organ or damaged organ. And then this is also either natural material or synthetic material. So this will try to improve the function of the body, or it can be carry the drug into the human body, or it can able to cure the cancer affected area by means of sending some sort of biomaterial into the area, and then you can able to irradiate the material externally so that it will be able to kill the disease part. So we can able to use as uh, drug, we can able to use as a tissue replacement partly or fully. We can able to improve the function of the body like that. This biomaterial can place various roles as far as the uh, human body is concerned. And then the replacement of the body part that has lost, for example, the total hip, hip joint, or bone joint, or bone, or spinal cord, or to improve the function of the heart, or to perform the bypass surgery, we are going to develop some porous material, the composite material as the slants. And then similarly, uh, you know about the capsules, they'll try to carry the drug. Those capsules made up of polymer, that is also the biomaterial. And then once the operation is performed, the doctor used to stitch that particular area, right? The stitches also, they are biomaterials. So they'll try to assist in healing the body of the human being. So if you see the examples, and then the synthetic amino organs are the scientists, they are developed in collaboration with the doctors, and then the scientists and the scientists are working in not only physics, even working in the area of the biology also. So this is not completely this is interdisciplinary area. So physics, chemistry, biology, and then the doctor, they'll try to collaborate and they'll try to work for developing the new material for biomedical applications. So for example, if we take heart, we can have the artificial valve which can able to develop by means of the biomaterial, pacemaker, artificial heart also. Similarly, eye are related, the ophthalmology related, the contact lenses, the intracorneal lenses, we are going to develop by means of the amorphous material like glass, the glass material we are using to develop these contact lenses, contact lenses. And then if you see the human body, there are hard tissues as well as the soft tissues. So as far as the soft tissues is concerned, the tissues related to eye, tissues related to ear, they are soft. They come under the category of soft. Then the muscles also will come under the soft. So the artificial stapes, the cochlear implants, which are there in the ear, so they are also developed by means of this biomaterial. And whereas the hard tissues like bone, like teeth, so there are, hard material. We require hard material, and here the physics play a crucial role. The mechanical properties are very very important, like the hardness, the flexural strength, the mechanical strength. So all these very very important as far as the development of the hard material is concerned. Similarly, the teeth also, either the filling material or you want to replace the teeth completely or partly. So we need to develop the biomaterial. So here we are having the ceramics, we are having the metals as the bone implants or the teeth implants. Similarly, kidney, if you take the kidneys, dialysis machine also is an example for the biomaterial, and then the bladder, the catheter, and then the stent. This comes under the category of the biomaterials useful for the bladder, and you can develop the artificial muscles also by means of the polymers, and then for the circulation of blood. So suppose some part of the blood vessel has damaged, partly or completely, can able to replace with artificial blood vessels, which is developed by means of once again the ceramic material. And suppose some part of the skin was burned or completely burned, we can able to develop the artificial skin, and we can able to completely replace the skin, or we can replace the part. These also developments of some of the polymer material. Like this, there are different types of biomaterials are there which can be used for the replacement of the organ completely or partly, or tissue partly or completely. These are some of the examples of the biomaterials are concerned. And see, we cannot use all the materials as biomaterials. If you want to use any metal as a biomaterial, it should possess some properties. For example, you take the biocompatible is the first thing. See, you can have metal, you can have ceramic, you can have glass, you can have polymer, you can have a composite. Any metal, if you want to use as a biomaterial, just like that you cannot use as you are keeping a book in the rack. It's not like that. So we need to check certain attributes, whether it is possessing the attributes or not. If it is succeeding, then you can able to use as a biomaterial. So it should be non-carcinogenic, it should be non-pyrogenic, it should be non-toxic, it should be non-allergic, it should be compatible, and it should be acceptable physiologically by the human body, and it should be non-inflammatory also. So if the material possesses these properties, then we can say you can use it as a biomaterial. So it should not be toxic. So if you are, replacing any part of the human body completely or partly, first of all, you need to check whether it is non-cancerogenic or not, non-allergenic or not, non-pyrogenic or not, non-toxic or not. See, according to the ISO standards, and I'll explain those things in detail in the coming slides. Suppose if you have any material and then if you want to confirm whether it's a toxic or not, so you need to feed to the bovine cells. So if your main material, is killing the cells, right? Then you cannot use as a biomaterial. So it should be non-toxic. It should not kill your cell lines. The bovine cells or whatever cells you are going to use, it should not kill. It should be non-toxic, means the viability of the cell should be there. And similarly, as I mentioned, it should have some mechanical properties. Whether you are developing the soft tissue or hard tissue, right, it must possess the physical characteristic like mechanical strength, the elasticity, the durability, the hardness, and then the manufacturability is also an important thing because you are going to mold into different shapes, right? So machinable is there, moldable is there, extrudable. These are the manufacturable properties. And similarly, the sterilizability also. So if you want to use it as a material, material as a biomaterial, you should possess all these properties: biocompatibility, sterilizability, physiological characteristics, and then manufacturability. Before testing all these things, first of all, we need to test whether the material what I developed is bioactive or not. So for that, we need to create an environment similar to that of the human body. You know about the blood plasma, right? So nobody will be ready to, allow to keep this material into the body just like that because we don't know whether it's toxic or non-toxic, whether it's acidic or non-acidic. So so nobody is ready to, allow to keep the material inside the human body. So we need to create an environment similar to that of the blood plasma, which is known as the stimulated body fluid. So that we are going to do in the lab. So we are going to follow a protocol, and according to protocol, we are going to prepare the stimulated body fluid with pH 7.4 in the atmosphere with various chemicals, which is also almost resembles the blood plasma. And then we are going to immerse our material into that blood plasma, and we are going to check whether the material is trying to react with the stimulated body fluid. If it reacts, what happens there is it will try to form a layer on the surface of the material. It means that there is a leaching of ions across the material from SPF to material to SPF. As a result, the reaction, as a result of the leaching, there will be formation of layer. So that we will try to confirm whether the material is bioactive or not. And if you want to confirm whether the material is bioactive or not, we are going to use various material characterization studies. The physics, when what we are talking about the biology, and now I am going to talk about the physics, right? So we are going to use the XRD, we are going to use the FTI, we are going to use the FESEM, we are going to use the degradation, erosion, all these studies we are going to do in the lab for these material. And from these tests, we are going to confirm whether the material is active or not. So that is the first test we are going to do. And after that, once the material is succeeding in those tests, we'll go for these type of studies like biocompatibility, the physical characteristics, sterilizability, and then manufacturability. So there are different types of, see, this biomaterial is not a new one. So years together, people are trying to develop different types of material. So many hospitals are there where people are trying to develop orthopedic implants, related to the bone, related to teeth, right? Years together. So there are different types of material like metals. Among metals, you have stainless steel, cobalt, alloys, titanium alloys, zirconium alloys. So many are there under the category of the metal. Similarly, under the category of the ceramics, we have the aluminum oxide, zirconia, calcium phosphate. Under the category of amorphous material like the glasses, we have the calcium phosphate glasses, we have the borosilicate glasses, we have silicophosphates. So many types of amorphous metals also there. Similarly, in order to develop the soft tissues, people are using the polymers. like silicones, polyethylene, polyvinyl chloride, polyurethane, polylactic acids, and not only these chemical based material, you can use some natural polymers also, like collagen, gelatins, elastin, silks to develop the biomaterials. So, as far as the polymers are concerned, I mentioned nylon, silicone, rubber, etc. People are using these material to develop the biomaterial like sutures. I mean, so in olden days, people try to use threads, right, to stitch after the operation. The doctors, I mean, they will try to operate, they will try to perform the open surgery, right? And once surgery over, they used to stitch the threads or some sort of wire, right? So after, I mean, few days of time, after a few days, maybe 1 week, 10 days, or 15 days, or 1 month, right? So they'll ask to visit the doctor so that they will try to remove the stitches, right? But nowadays, people are not using those type of stitches. They are using these stitches which are developed by means of the polymers, and then no need to visit the doctor for I mean the opening the stitches. So automatically they try to degrade with the temperature of the human body. So that is regarding the stitches, and similarly the blood vessels, not only the blood vessels, the soft tissues related to ear, soft tissues related to nose, the hip sockets, we can able to develop by means of these polymers because they are easy to fabricate, they are resilient. The disadvantage is they are not that much strong, they may degrade as the time goes. So that's why we are going to use these polymers for developing the soft tissues. And similarly, if you want to develop the hard tissues like teeth implant, the bone implant, I mean to say the dental orthopedic implants, uh, people are using the metals like titanium, nitalites, cobalt chromium alloys, silver, gold, stainless steel because they're strong, they're rough, they're ductile. But the difficulty is that they may corrode. They are dense and difficult to carry also because they are more weight. Uh, and similarly, we can able to use the ceramic to develop uh, dental as well as the orthopedic implant because they are having the mechanical property as that of the metals. Uh, that is the advantage. And more thing is that they won't corrode easily as that of the metals, and they are not that much weight compared to metals. That's why a lot of research work is going on in ceramics, where people are developing new material because they are very much compatible compared to the other materials. Similarly, there is one more area where a lot of research work is going on related to the materials is composites, right? As aware of that, composite is made up of two or more material where there'll be matrix and into which we can able to reinforce different types of the materials in terms of particles, wires, rods, whatever it may be. So they are polymer metallic composites, they are glass metallic composites, they are metallic metallic composites, carbon metallic composites. So many types of composites are say where you can able to use polymer as a matrix, metal as a matrix, ceramic as a matrix, into which you can able to reinforce different types of material to enhance the properties of the material. And these are some of the replacements related to the heart tissues, the hip replacements. You can see here. Can you able to see the PPT? Hello.
Sir?
Can you able to see?
Seen, sir.
Yeah. So here you can able to see this ceramic ball, the metallic ball. This is artificially developed the implant. This is a metallic cup. This is the metallic stuff. We can able to use even the ceramic also. So what I'm going to say here, these are some of the artificially developed orthopedic implants with metal as well as the ceramic. So these implants, this is an X-ray after implanting this metal as well as the ceramic ball into the human body. So these are the dental implants. This is the metallic screws, filling material, and this is the teeth which is made up of a ceramic. So I'm talking about the synthetic biomaterial. So we can have the polymer-based biomaterial which can use for the drug delivery devices. For example, you take the capsule which is made up of polymer, which will carry the medicine to the human body. Similarly, you can able to develop the artificial skin, the artificial cartilage, the ocular implant. Ocular means related to the eye, the contact lenses. Not only polymers, even you can able to use glass also to develop this material. This is one category of biometric. Similarly, metals I mentioned. So we can able to develop the orthopedic screws, the fixation with metals like cobalt alloy, zirconium, nickel, titanium. So many metals and the metallic alloys are there. We can able to use both for orthopedic as well as the dental applications. And similarly, we are having the ceramics like calcium phosphate, calcium silicate, dicalcium phosphate. So many ceramics are very high temperature material, porous material, and they are more, very high by compatible. That's why people are more interest toward this ceramic material. We can able to replace the bone, we can able to replace the dental implants, we can develop the artificial blood vessels, the stents, the heart valves. So we have to thank the then President of India, Dr. Abdul Kalam. We have developed the artificial stents with the ceramics when we work in DRDL or DRD. And similarly, we can able to develop some implant microelectrodes or biosensors, artificial sensors which can able to replace tongue or nose, right, for smelling or for tasting with these semiconductor material and then composite material. So we can develop composite based implantable microelectrodes, semiconductor based implant electrodes as well as the biosensors. So these are the some of the biomaterial for bone tissue engineering applications. So if you see this, there are three generations here. First generation, uh, which are inert, so they won't interact with the tissue or organ in the human body, right? It's just like a book in the rack. So we are going to, this is the first generation people are developed for orthopedic, implants. So alumina, zirconia, metal biomaterials, polythene, these are the first generation, and you can see the images of the first generation biomaterials here. And second generation, what you are working now is bioactive and then bioresorbable. So these material, whether it may be glass, glass ceramic, or composite, what it may be, right? So it will try to interact with the tissue or organ, and then it will try to develop, right, a bond between the metal and then the tissue. So this is second generation. In this category, we have the bioactive and then bioresorbable material. So we can see some of the ceramics, what you have developed in our lab. This is related to, the second one is related to our material. And the third generation, where a lot of research work is going on, and this is, the emerging area. So there is large scope for working in this material, both the second and then third generation. So this second generation, the metal are, we are also working in this area. The generally there is metal are porous in nature. They are advanced by ceramics. We can use mesoporous silica and base material. You can use the organic and inorganic beds. You can use the template gases also. So all these are the metallic amine structures which are developed in our institute by the mechanical department, where they have the 3D printing. So by means of it, they are going to develop this type of material. So as I mentioned earlier, so material will be interacting, material will be just like have the morphological interaction, material can have the interfacial bonding, metal and toxic. It will try to decay and help the tissue to grow. So there are different types of material are there which will try to respond to the implants which are there in the human body. So the third generation material what people are trying to develop, they try to help the tissue to grow. Suppose if you develop material and then if you use as a plant, what happens the time goes the material will decay and then helps the natural tissue to grow. That is the resorbable material what people are talking about now, right? So that type of material also people are developing. So this is regarding the tissue response to the implants. If the material what you are developing is toxic in nature, you cannot use as an implant material because it will try to destroy the tissue and as a result the patient may die also. So the basic requirement is whatever material you are trying to develop, it should be non-toxic in nature. If it's toxic, what happens? The surrounding tissue will try to die. That is very, very important. And this is regarding the plot between the implant time and the bioactivity. Suppose if it is a inert material, it won't interact with the tissue in the human body. So it will be just like a metallic implant, right? The bone. We used to have the bone replacement or the screw replacement, which is made up of metal. So the implant time may be years. So we cannot remove every 1 week or every 1 month. So it should be per few years. Whereas the resorbable material, see, within days it will decay and then it will help in having tissue to grow. So it will be for a few months only, few days to few months. And the bioactive material what we are developing, it will from few days, few months to years. And the porous material will be having the more time. So this is the material where a lot of work is going on. The ceramic material, the porous material, which will be interact with the living tissue and helps the tissue to grow. Usually, we used to follow this protocol. I mean, people are working in the biomaterial to translate into the new material for new applications. So they are trying to follow this particular protocol. The first step, what you are doing is development of implant materials and this characterization. So by means of melt quenching technique, by means of soil gel, by means of hydrothermal technique, different types of technique we are trying to adopt, and then we are going to develop new material either with chemicals or by means of the recycling waste. That is first step where we are going to develop the material, and after developing the material we are going to do some characterization like the XRD to confirm whether this material is a amorphous material or crystalline material, and then the function groups we are going to check it out by means of the FTIR, the morphology, the size, shape we are going to confirm it by means of FESM, the PS studies we are going to do, the degradation studies we are going to do it, the so many types of physical studies we are going to do, and similarly we are going to uh, measure the mechanical properties like hardness, the mechanical strength, the flexural strength, the ductility, so on and so forth. Because our interest is to develop the hard tissues like teeth and then the bone. So we are concentrating more on the hard tissue applications. That's why I'm mentioning about the mechanical properties. So the first step we are doing in our lab, and then the second one we are doing in our lab in collaboration with the few facilities are there in our lab, and the few we are trying to taking the help of the biotechnology and then the biochemistry department of University of Hyderabad. So where you are perform the cytotoxicity, the cell culture, the genotoxicity, immunoblotting, and then we are trying to get the fluorescence images and the confocal images of the material. That is the second step. Even the bioactivity are we are trying to do in our lab. So we have the facilities also here. So that is the second step. So we need to understand in vitro test and then in vivo studies. So in vitro means it will be outside the human body. So as I mentioned earlier, so you know about the blood plasma. So we are going to create a similar environment as that of the blood plasma outside the human body, which is nothing but the stimulated body fluid. So by means of following a protocol, you are trying to develop the stimulated body fluid, and then this stimulated body fluid, we are going to immerse our material, and we are going to test whether our material is bioactive or not. So we are going to confirm it by means of FTR, XRD. I'll try to show these results of some of our material we are developing in the lab. Similarly, the cytotoxicity, we are using the MG63 sarcoma, osteosarcoma cells, the bovine cells, and we have feed our sample with those cells. And then after 24 hours, 48 hours, we are going to test how many salines are alive. So that also we are going to do by means of the absorption studies, once again the physics. So absorption studies we are going to do, and then we are going to get the spectra. With the spectra, we can able to see the viability of the cells. So according to ISO standard, the viability of the salines after 24 hours of 48 hours exposure, the availability is about 70%. Then the material is said to be non-toxic in nature. Suppose the viability of the cells say less than 70, then the material should to be toxic and we cannot use the material as a biomaterial. So that is the confirmation we are going to do it by means of performing the cytotoxicity test. Suppose there are 100 cells we are feeding to our sample. So after 24 hours, this is an example only. After 24 hours or 48 hours, if there are only 30 cells alive and 70 are dead, then it means we cannot use the material as a biomaterial because it is toxic. Because of toxicity, the cells are died. So if there are 80, 90 cells are there, even after the exposure of 48 hours, then you can say the material is non-toxic. So that is like that we are going to perform the studies in collaboration with the University of Hyderabad Biochemistry Department. So that is the second step, and we have completed the second step, and the third step is in vivo. So we are going to do the animal modeling. Shortly we are going to do in collaboration with the University of Hyderabad. So we can do the rabbit modeling or the mouse modeling here. So we are going to implant the material into the mouse. Basically, you are working for the bone implant, and here you are going to see the tissue viability, the histology, the inflammatory cytokines and toxic studies of nanosize wear debris. So we are going to we didn't start. We are going to start shortly about this particular thing, and then see, it is not that much simple because you need to get the permission, and then you need to follow some protocol because nobody will be ready to allow your material to the animals also. So we need to get the permission. So that is the third step, and then the once you succeed in the in your implantation, then it will go for the clinical trials. So clinical efficacy, I think you might have heard about during this corona, right? The Bharat Biotech and then the other pharmaceutical industry, they developed the vaccination. So because of the necessity, the protocols they done at a faster rate, and then the drug was released immediately. But it is not that much easy to get the permission, so we need to spend years together to carry out the third step and the fourth step. So clinical efficacy is the which is a part of the fourth step. The clinical feasibility also a very important thing, and finally the human trials. So once you succeed, then you can develop your product not only at the lab scale and at the market level you can able to develop and they can release into the market. So this is the scenario as far as the development of biomaterial is concerned. I can say the brief overview of the steps involved in the translation of new developed biomaterials. So there are different types of biomaterials are there. We are working for several years, almost for last 15, 16 years, we are working for these materials. We are developing new materials for the new applications. So we have started with the great scientist, Professor Hench, as a reference. So he is the, I can say, the grandfather of these biomaterials. So this is the H composition, 45 is glass. So the composition is 45% of silica, 24% of calcium oxide, 24% of sodium, and then the phosphate. So that's the base, and with the help of that, we have developed different types of biomaterial, glass ceramics, and then the ceramics. So we are having different types of material like calcium phosphate based, like calcium phosphate, then hydroxyapatite. Then the calcium silicate base. So this is the area what I mean you're working, and for the first material, I mean we have developed with recycling waste in our material, in our lab. So for that, we got the Indian patent in the year 2021. We got the Indian patent for the development of elastomite from the recycling waste. So we developed the elastomite and the tricalcium, diapside, the recycling waste. Similarly, we are working. We have been working for several years on the bullet based glass and the glass ceramics for this biomedical applications is concerned. So a biomaterial can be a single crystalline material, or polycrystalline material, or glass ceramic, or composite. It can be any one of these materials. So this is the guy, I mean, who is inspiration for us is Professor Hench. So according to him, a biomaterial is one that elicits a specific biological response at the interface of the material, which results in the formation of bond between the tissue and then the material. So this is a triangle which helps to view a new composition, right, for a new material. So from this you can understand the active material, inert material, dissolving material, and the material is now going to form a glass. So this is the triangle. From this we can able to decide the composition also. So I'll try to share, or I'll try to discuss some of the results of our students which are working for last several years, for the last 10 years. Right. So we have developed this borosilicate glass doped with zirconium, and we have used zirconium because it's a best implant material for our tissue applications. So we have choose this material because of its strength, the fracture toughness, good chemical and then dimensional stability, and then it is having the length smallest similar to that of the hard tissue, the metallic implant like stainless steel. Because of this reason, we took zircon as additive, and then we are incorporating the basic composition and we develop the material. So the mechanism is simple. The process is very simple. If you have a furnace and then motor and piston, few chemicals, you can able to develop the material. So these are the chemicals we are used. We weight by microbalance, and then so this is the development of material at lab scale. So we can develop at the large scale also. For that we require the large machinery. So we have weighed the material. We are collected in a piston and motor. We are grind it, make it a fine powder, and this fine powder of this composition, borosilicate, sodium zirconate, we are collected in a motor piston. We make it fine powder, and then these are collected in a platinum crucible. So we keep in a furnace, right? So we are increase the temperature up to its melting point. We stay for a half an hour, 1 hour, so that the material completely melts. So once it completely melts, you will quench it. And finally, you are going to cool it, and you are going to pour this molten solution onto the preheated brass plate with some molds. So we'll get this type of glass, right? Then we're going to polish it, grind and then polish it for the characteristics. So these are the characteristic techniques what you have in the knowledge shoot. XRD, FTR, PSM, right? Physics department is also having one APSM. Recently we purchased that APSM under fist. We are having FTR also. We are having UVisible also in our department. So we are using different types of characterization techniques like XRD for formation of the appetite layer. We are using the FTR for the functional and then characteristic bonds. As I mentioned, we are using FESEM in our X department to study the surface morphology of the material, and then EDAX we are using for the elemental analysis. And the mechanical department is having universal testing machine. Vickers harness tester, by means of which you are testing the hardness and then the other mechanical properties of the material. Right. So as I mentioned, we are doing the in vitro studies first. This is a lab scale. Uh, this is similar to that of the blood plasma. This is known as the SBF. So which is known as in vitro means in outside the human body. So we are going to test whether the material is active or not. So this is a rapid and this is a low cost. This is the first step to understand the physiological system. As I mentioned, so we are going to test the bonding between the tissue and then the implant by means of this particular study. So we are creating the environment similar to that of the blood plasma, and then into which you are going to immerse our material. So there will be interaction or exchange of ions between the stimulated body fluid and the material body fluid. As a result, there will be formation of layer. So this is the blood plasma. This is the composition, the ionic composition of the blood plasma, and this is what you have prepared in our lab. This is the stimulated body fluid, which is almost resembles the blood plasma. So we are going to take it as a reference and we are going to check it out. So here, ion exchange, change of pH, the formation of surface hydroxide split. This is the primary step to test whether our material is bioactive or not. So this is the first thing, and see, so we are preparing the stimulated body fluid, and into which we are going to immerse our material, powder or pellet or raw water maybe, and which resemble the blood plasma. So 37 plus or minus 0.5 degrees Celsius, and the pH is about 7.4. Right. So this is the first thing. I'll show you. Yeah. So this is regarding the glass. So this is XRD of the glass. So you don't have a permanent peak. It confirms that the material what you prepared is glass in nature. This is before immersion. When you prepare the glass and then you are going to check it out. Now, after immersion of your material into the stimulated body fluid for 1 hour, for 1 day, for 1 week, or for 5 days, or 21 days, whatever it may be. So immerse your material into this SBF, and after 1 week of time, you remove the material, and if you record the XRD, you will get the pattern like this. So these are the crystalline peaks. These crystalline peaks confirms that there is a formation of layer on the surface of your material. So this crystalline peak is corresponding to calcium phosphate. This is the hydroxyapatite layer. So this layer is formed because of the exchange of ions between SBF and then your material. So similarly, this is the XRD of your material record after 15 days of time. See, the peak intensity is increasing. That means the crystallinity is trying to increase. And similarly, this is the FTIR before immersion of your material. So this tells about the functional groups of your material which is consisting of. Now after immersing your material into SBF, you can see few peaks, 560, 600. The doublets indicates that this is related to calcium phosphate. So this also confirms that there is a hydroxyapatite layer which is formed on the surface. So not only with the XRD, we are confirming that these crystalline peaks are corresponding to hydroxyapatite layer or formation of layer on the surface. I can say the bioactive nature of your material. Even With FTR also, we can able to confirm whether the metal is biactive or not by means of this functional groups, this functional groups. Similarly, if you see here, this is a SEM image of your material. This is before immersion. This is after immersion of 5 days and 15 days. So if you see a 15 days of immersion, you can see the precipitate. Why precipitate? So this is the clear evidence of the formation of layer on the surface of our material. So we can say that your metal is bioactive in nature. Similarly, we have done the hardness test. So see, it is increasing with the zirconium content. We are testing. So we are doing the mechanical studies, compressive strength, fracture toughness, hardness, and so on and so forth. So you can observe from this graph, with bar graph, with increase in the zirconium content, the hardness also increasing. So from 560 megapascal to 630 megapascal. And one more thing I mentioned about the toxicity, whether the material is toxic or not, we can test with this protocol. So we are going to take our material and we are going to feed to the cells. So here you are using the human osteosarcoma cells, which is known as MG63 cells. And then this is a protocol steps you are going to follow, right? And then with this formula, we are going to check the viability of the cells. You see here, right? So these bar graphs, you see, if you observe carefully, so the viability of the cells is above, in all the composition, it above 70%. If you see this, it is 80, and in some cases it's 100. So it is 75 to 90. So in all cases, so Z0 means without zirconium, Z1 is 1% of zirconium, 3 is 3% of zirconium, 5 is 5%. So with increasing the zirconium, we can able to observe that the viability is above 70. So according to ISO standards, right, if the viability of the cells is above 70%, then material should to be non-toxic in nature. See, the lowest composition of metal is 50 micrograms per ml to 1000 microgram ml. So for the higher concentration also, we observe that our metal is non-toxic in nature. And you can see the optical image of this. So there are some flakes. These flakes are live cells. These flakes are live cells. So even for 1000 grams also, we can observe live cells in the image, the optical image. So this confirms that the material what I develop is non-toxic in nature. Similarly, you are doped with titanium, and you have done our studies. And one more important thing here is a confocal image. So this confocal image, it you can see the cell here. You can even at the higher concentration also, the cells are alive. So this confirms that the metal is non-toxic in nature. So we have published these results in different journals, and this is regarding the amorphous material. What I explained so far is amorphous material. Similarly, we develop the crystalline material by soil well, by hydrothermal, by combustion. So different methods you are using and developing. But here we are trying to take the natural resources. Like we are taking the rice husk, which is a major source of silica. So all these are the recycling waste. This is the agriculture waste. This is the food waste. This is the industrial waste. All these are the biomass, bio waste. So if you take the XRF of this material, you can able to find a lot of minerals inside this. For example, if you take rice husk, the major constituent rice husk is the silica. It is about 98%. And if you take eggshell, the food waste, So the major constant 99% is the calcium carbonate. If you heat it, dissociate into calcium oxide and carbon dioxide. So if you heat it, the carbon dioxide will try to evaporate, will try to have only the calcium oxide. And similarly, peanut also is the source for silica. Coconut coir also source for silica. This fly ash is not only having the silica, carbon, and calcium oxide, will having other the minerals also. So we have chosen these materials, the food waste, agriculture waste. See, our motto is waste to wealth. So we are developing bio-waste derived calcium silicate cost-effective material, which is a better alternative for conventional ceramics, not only for tissue development, for the energy storage application, for display applications, for optoelectronic application. So this is why you are choosing the advantage of this material is they're bioactive, they're biocompatible, they're stable, they're biodegradable, they're having the mechanical properties, they induce the astral cells even for the proliferation also. You can able to use for the proliferation of the tissue also by means of using this material. So this is a protocol we followed and we developed the material. For this only we got the Indian patent in 2021. So with the help of this method, right, we developed the calcium silicate, and this is the TGTTA, which tells the crystalline temperature of a material, and by optimizing the temperature, we got the structure, which is the volatile structure, which is crystalline material. This is the XRD, which confirms the material is crystalline nature. Right now, we have developed this material. We made a pellet, and then we immerse this material in a simulated body fluid. And after immersion of 3 days, we record the XRD. After 7 days of immersion, record the XRD. After 14 days of immersion, record the XRD, and then 21 days after immersion, record the XRD. We can see that there are crystalline peaks at 0, 0, 2, 211, 222. All these peaks are corresponding to hydroxyapatite, not the material. So this confirms that there is a leaching of ions between the material and then simulated body fluid. As a result, there is a formation of layer, which confirms that the metal is bioactive in nature. This is from XRD you are confirming. And similarly, if you see here, the SBF emulsion and then recording of a CM, right? We can see the lower precipitates here, right? This precipitates confirm there is a formation of layer on the surface. Even we can able to find or identify the elements with EDS, and from EDS we can see that there will be calcium and there will be phosphate, and with the immersion time, right, the calcium phosphate ratio also increasing. So the calcium phosphate ratio is between 1.6 to 1.66. We can say that it is resembles the bone. So if you see the bone, I mean the calcium phosphate ratio in bone is about 1.66. So the material what you are developing is having the calcium phosphate is about 1.66. That's why you can able to use this material to develop the bone. And if you see the cross-sectional view of our material, see there is a formation of layer on the surface of the substrate. So we have measured the thickness. It is about 49.09 micrometer to 109. So it is increasing with the duration of the time. The formation of the layer thickness is increasing. Similarly, we can confirm the layer formation with FTR also. And not only that, we are trying to do the pH studies also. If you see here, the pH of the SPF is about 7.4, but with the immersion time, you can see here the pH is increasing and reaching the saturation point. So this is happening because of the exchange of ions between the SBF and then the material. And similarly, you can able to see the degradation studies, how much it is distribute. So this also confirms the formation of layer, or you can say that the bioactive nature of the material. So there are various methods to confirm whether the material is bioactive or not. And then the second step, what I mentioned in the beginning of my discussion, is about the cell viability. So here we are done for different concentrations, 50 microparamilla per material to 1000 macro. Even we are having 2000, 2500, 5000 microparamilla also. So even at that higher concentration also, our metal is having the viability more than 70%. So it is almost on 90, even over 90 also. So which confirms that the metal is non-toxic in nature. And I mentioned in the beginning about the mechanical properties. So the microhornets, the compressive strength we measure. So the beauty of these metal is they'll be porous, they'll be bioactive, even they having the better mechanical properties also. That's why a lot of research work is going on to develop this metal, to develop even the synthetic organs also, where I mean we can use different methods to make the develop the synthetic organ by means of using the 3D printing also. That is the latest area where a lot of scope is there. So we can see the hardness, it is varying from 18.74 to 20.52. So its mean hardness is about 20.14. Similarly, the compressive strength, the mean value is about 40.77. So these results are published. And similarly, we developed the silver doped vollasnate also. So this is the silver doped vollasnate. And you can see here, not only you can confirm with the XRD, the formation of layer, even with FDP also you can able to confirm the formation of layer. Even with the FECM, see here, there are white precipitates which are forming on the surface. But different structures we can able to see here. The plate-like structures we can able to see here, the calcium phosphates on the surface of the material. So which confirm the material is bioactive in nature. We can confirm by means of the observation of the change in pH value, the degradation also. And not only the cytocompatibility bioactivity, even I told you about the non-allergic. So that non-allergic, we are going to check it by means of doing the antimicrobial, antibacterial studies, antimicrobial studies. So here we are going to test with different bacteria, E. coli, SRS. So we are test with two different bacteria, and we are confirming that our metal is inhibiting. This is not allergic. So see here, there will be no zone, no man zone here, right? So it is inhibiting. It is not reacting. So it is not allergic. So we are done with 2, we can do with 10 or 20 also. If the availability of bacteria is there, we can able to. So silver is mostly inhibiting. It is excellently inhibited, right? You can see the Norman zone here with the silver content. So the thickness, the diameter is also increasing. So silver is best antimicrobial agent which will try to inhibit the pathogens such as E. coli. So from this you can confirm that metal is non-allergic or dissuading the antimicrobial activity. So, so that is the second step. Now the third step is the in vivo, which is the animal experimental. So we need a bit approximation to the human body. So it will demand a lot of demand protocols because we need to take the permission. So there is an Animal Welfare Act, so we need to get the permission. So it is very difficult to get the permission. And this is a right model for animal modeling, approximately for environment. This is second step prior to the clinical trial. And then we have the clinical trial. So these are the scholars who has completed their PhD. So this guy is doing his PDF in Israel. So others have been working in different universities. And this guy is presently working with me, and three more are there. I'll try to, if time is there, I'll try to show those results also. These are the some of the material which we are developing for drug delivery applications. So here we are using chitosan solution and then our glass powder and ibuprofen. We make it a paste, and then we'll try to make the phosphate cement, and we'll try to check the antivirus property, and then you are going to check the in vitro biovalidation, and then the drug first you are going to set, right, and then you are going to do the drug delivery studies by means of this material with the anti-drug, the antibiotic like ibuprofen. So we are doing with different drugs, and you are going to check whether our material can be used as a drug delivery device or not with the help of these studies. So these drug delivery studies we are doing with different types of concentration of our material. So this is regarding to confirm whether the material is used as a drug delivery. So we are using the UV spectrophotometer FDR for these studies. So this will try to check whether the drug release or not. So after 48 of immersion, right, the ibuprofen release about 98.073% of the drug into the pH solution. So we can say that it is sustained release of ibuprofen into the body with the incubation of this much. It's also one type of application of our material. And not only that, even as I mentioned, we are using the I told about the tissue engineering, I told you about the drug delivery. Similarly, we are trying to develop these material. We are taking this material like eggshell, peanut shell, sugarcane baggage, coconuts, EGBS, rices, flash, corn cob, all these things. Because they are the major sources of different material, and with those material trying to develop the calcium and calcium silicate based glass and ceramics, right? So because they are available in bulk, even at low cost. So, so we are develop different types of structures with this industrial waste material like flash, GGPS. We use these sources of silica, calcium oxide, iron oxide, magnesium oxide. So many minerals are there, but the major constituents of these fly ash and the granulated blast slag furnace, right? So these are the industrial waste material. So we have a lot of industries here. The power stations, the thermal power stations are there near Ramagundam, Bhupalpalli. I mean, we have a lot of, industrial waste people are going to produce, and we are, extracting the silica, the calcium oxide, the other material from this recycling waste, and with help of solid hydrothermal, we are developing uh, different types of calcium silicate based. So there are so many types of wide variety of structures are there, like calcium silicate, bactite, acarbonite, diapside. So many structures are there. These are the sources of different amino applications. So these are the host material. So with the help of this host material, we can able to study different types of properties, and from that we can able to develop different types of devices also. So we can able to use this as a host for photoluminescence because we can able to see the deep emission, red emission at 690 these 690 nanometers when you excite with 370. So this will be used as a photoluminescent material and can able to develop the display device, and even you can able to use this material for latent printing applications also. One of my students also developed this material for latent fingerprint applications. And similarly, we are trying to develop a anode material, test material for the supercapacitor applications. We are doing the cyclic photometer studies and the CD curves, and we will determine about 158.54 per gram or 139.5 per gram. So this corresponds to 10 millivolts per second and 1 ampere per gram scan rate. So we are trying to develop even the anode material for the supercapacitor application, and with the help of this material, we made a capacitor by making these stacks, and then we are used to glow some of the electronic gadgets like the LEDs in series, then some electronic gadgets like the cell phones, and then even the batteries, even what you call the calculator also. So you are at the development set, you want to increase the charging time and discharging time. So by means of using this material as a storage, energy storage material. So we follow this protocol to get the material, and then we are trying to develop the activities of active material water developed. So we are using this active material in this ratio with carbon black, PVDF, and then active material 1:1:1 ratio. And then a nickel form we are going to put with 3 electrode. One is a counter electrode, reference electrode, and working electrode. We are trying to, we are using aluminum, we are using nickel, and different types of electrodes we are using, and we are checking. And these are the some of the characteristics we have done to see the structure of our material, because we are using the recycling waste consisting of a lot of minerals. So with the temperature, there may be phase transformation. There will you may get different structures, right? And at different temperature, you may get different structure. Because of that, the properties will tend to change, right? And then you can able to use it for different types of applications. So we have done the porosity studies, and then the pore volume, the pore radius we have measured with PET. So because we have the facility in the chemistry department, we have done the surface morphology also, because as far as the supercapacitor application is concerned, we need to have the high power density, energy density, right? For that, the surface morphology is very, very important. So that's why we have done this BET studies. And so I told you about the constants of the fly ash and GGBS. See here, so we have done the XRF for fly ash. So it is consisting of major component SiO2 63%, then aluminum oxide 23.3, and then next one is iron oxide, then calcium oxide. Other they are the trace elements. If you take GGBS, it is 26.1 silica, 13.4 aluminum. The major component is calcium oxide, 45. Calcium oxide, the major one is 45.8 in GGBS. So in a fly ash, silica is the major, GGBS, calcium oxide is the major. So we are trying to take these two as the sources, and by optimizing the temperature, we are optimizing the structure also. So this ratio is beneficial. Silica aluminum ratio is beneficial for the electro. See, whatever studies you want to do, first of all, you need to understand the role of each and every constitution. Constitution, we can able to do our work effectively, and there will be some scope for us to develop a new material and for new applications. So here, after developing the material, we observe that the mass ratio of silica aluminum is very high. and that is very much essential, beneficial for the chemical properties, which will enhance the high surface area, the band charging, transfer resistance, high charging, and discharging time. So we done the cyclic photometry studies. We have the electrochemical workstation in the department. So we have done the galvanic charge discharge, and we have done the electrochemical elements analysis also. And then the diffusion chemical capacitance current contributions also we have done. And then we made the device, and with the device we have grown the LEDs. We have charged the cell, I mean the watch and then the calculator. So we have blown light up 4 LEDs more than 24 seconds. Digital loss for 51 seconds. So calculator for 30 seconds. So we are trying to improve by means of using the various combinations. So we are trying to develop the anode cathode material. It's cost aminophilic material. So we have filed the patent for this also. So many papers, published in various journals. So these are the other students who are working at present with me. Ms. Pooja and then Mr. Gangadhar, they are working with me. Present. So I thank the organizers for giving me the opportunity to share my research. So there's a part, so many things are there because of the time. I mean, I restrict myself, right, to give one or two examples and what has been carried out in our department, in our, especially in our lab. So we have facilities like the synthesis facilities are there with me, and then the department we are having FTAR, we are having usable analysis spectrophotometer, we are having FEACM, furnaces are there, few coating units are there, like CBD is also there, chemical vapor is also the department. So there will be a charge, right? On the charge basis, it will be allowed for anybody can able. If you have any samples, right, you can send them by means of. Just go to the website. There you can find the charges for each characterization, right? So you can book your slot and they can send your sample for the characterization. And if you have anything related to this presentation, you can interact me anytime. So the mail, you can for the mail and for other contacts, you can see the website. You can have and find the details. So I thank the organizers for giving the opportunity and thank all of you for your patience. To listen.
Thank you, sir.
Thank you very much. So open for discussion. If you have any question, ask me.
So, one participant was asking one question, sir. Can synthetic biomaterial be used in knee implants?
Yes, yes. So many are there. So because of time, I didn't show. We have knee implants, we have bone screws, bone plates, bone filling material, teeth implants like teeth filling material. So many are there. Made up of metals, ceramics, glass ceramics.
Okay, sir. Thank you, sir. Now it's vote of thanks time, sir. It gives me immense pleasure to propose vote of thanks. Firstly, I take the privilege to thank our management for encouraging us to conduct the FDP successfully. My sincere thanks to our principal for her guidance and support in organizing the sessions. My heartfelt thanks to our HOD Madam Dr. G. Haripriya for her constant involvement and cooperation. On behalf of our institution, I thank all our eminent resource persons who have accepted to be a part of our FDP and also for delivering informative sessions that was very beneficial both for research students and faculty members. I thank the staff and technical team for their efforts and participations during the 6 days of this FDP. My special thanks to our resource person, Prof.Dr.P.Abdul Azeem, for a brilliant and informative session on
Definitely.
fabrication of amorphous crystalline material for tissue engineering applications.
Okay.
Last but not least, I
Bhushan?
thank the participants from other colleagues
Okay,
who
sir.
joined us in making all the 6 days run successfully. Once again, thank you, come one and all. Thank you, sir.
Okay, bye.